Hello and welcome to this video. We're going to be talking about geometric series. This is aligned with Mathematics Analysis and Approaches Standard 1.3. So what happens if we add the terms of a geometric sequence? Let's look at an example. Take this sequence here, 3 to the n minus 1. We see that our ratio is 3 and we can write out the first, let's say 6 terms. Plug in n equals 1 and you're going to get 1 here. Then 1 times 3 is 3, 3 times 3 is 9, 27, 81, and 273. So we take these and we're going to add them together. And we're going to try and figure out what is the sum, and we let S be sum. To figure that out without having to add all these terms, because the sequence could be much, much longer, we're going to use a fancy geometric trick to actually quickly figure it out. So here's how we do it. We take our sequence and we're actually going to multiply it by 3. And we choose 3 because that was our common ratio. When we do that, we notice that it really just moves the series over a term. And so each of these is multiplied by 3, but now you've got these like terms here. So if we subtract these two sequences, s minus 3s, all these like terms cancel. And now we're just left with the first one and the last one. So we have 1 minus 729 equals s minus 3s. We can easily simplify this to be negative 728 equals negative 2s. Divide by negative 2 and we get the sum must be 364. So that same trick can be used no matter how long the sequence is. And in a second we're going to generalize this to any geometric sequence. So we can use the same idea from the previous slide in general terms to derive the formula for the sum of a geometric series. And geometric series is what it's called when you add all the terms of a geometric sequence. So here we have our first term. The next one is just going to be that one times r, and then that one times r again, which gives you r squared, so on and so on, all the way to u1 times r to the n minus 1, and we let that equal s. Then we're going to multiply that whole series by r, our common ratio, and we get this new one, u1r squared, so on and so on. All of these terms again match, except for the last one of the second one and the first one of the first one of the first series. All those other terms are going to cancel, and so you're left with just u1 minus u1r to the n, and then you've got s minus rs. You can solve this equation for s, undistribute the u1, so you get u1 times 1 minus rn, undistribute the s, and then divide by 1 minus r, and this is the formula that you get. The first term times 1 minus the ratio to the nth power, where n is how many terms you have, divided by 1 minus ratio equals your sum. So as the series grows, depending on the values of the common ratio, different things happen as it tends towards infinity. So if r is a big number greater than 1, and it can be positive or negative, like negative 2 or 3 or negative 4, or even a fraction, 5 over 4, as long as it's bigger than 1, we get something called exponential growth, which as you go on to infinity diverges, and we call this a divergent series. So we write it with summation notation from 1 to infinity, and we know that this is the formula that we just derived. If r is a number bigger than 1, then as n goes to infinity, r will go to infinity. In other words, this whole thing is going to get extremely big and go towards infinity. So this is not really that interesting. We just call that a divergent series, and we're not going to actually solve for the summation, only whenever it's a finite number of terms. So what happens if we have r less than the absolute value of 1? So that means that r is between negative 1 and positive 1. We're thinking of r as being a decimal, less than 1, like 0.1 or 0.15, or the negative version of that, negative 1/2, negative 1/3, anything between positive 1 and negative 1. So if that happens, we have a term that approaches 0, and the series actually converges to a value, and we call that a convergent series. So this term here, Rn, is going to tend towards 0. You can think about it with the series 1/2. Let's say the ratio is 1/2. The next one would be 1/2 times 1/2, which is 1/4, and then 1/8, 1/16, so on and so on. It's going to get closer and closer to 0, smaller and smaller. So this Rn term is going to approach 0, which means that the sum is going to approach u1 divided by 1 minus r. So if we have a series where r is less than the absolute value of 1, then we know the sum is going to be u1 divided by 1 minus r. Here are two examples to illustrate the idea. If we have a series where r is a number greater than 1, the absolute value of 1, in this case 2, these numbers are going to get bigger and bigger as they go along, and our series is going to go towards infinity as the number of terms goes towards infinity. But if our ratio is less than 1, like in this case 1/2, as we tend towards infinity, these numbers are going to get smaller and smaller, and it's actually going to equal something. In this case, it's going to be 1 divided by 1 minus 1/2, which is actually 2. So if you add all the infinite terms here, it will equal 2. Let's try a practice example using the formula we derived. So a geometric series has a first term of 3 and a common ratio of 2. Find the sum of the first 5 terms. Let's write out what we know. The first term is 3, the common ratio is 2, and we need to find the sum of the first 5 terms. Let's remember that our formula for the sum, in this case our ratio is bigger than 1, so we're going to use the first formula, u1 times 1 minus r to the n divided by 1 minus r. We have all the information we need, so we can just plug in and solve. u1 is going to be 3, 1 minus my ratio is 2 to the 5th power, all divided by 1 minus 2. This is going to give me 3 times 1 minus 2 to the 5th power. 2 times 2 is 4, times 2 is 8, 16, 32. All that's divided by negative 1. And then we simplify the top, that gives us negative 93 divided by negative 1. And that's going to be 93, so our sum is 93. Okay, calculate the geometric series given below by this summation. So we see that it's tending towards infinity, and we also see that our ratio is less than the absolute value of 1. So we know that we're going to use our second derived formula, which is u1 divided by 1 minus r. So my u1 here is going to be 2 times 1/2 to the 1 power. That's going to be 1. And then my r, or my ratio, is 1/2. So now I can figure out the sum is going to equal 1 divided by 1 minus 1/2, which is 1 over 1/2, which equals 2. So my sum is 2. Find two possible sequences where the sum of the first 2 terms is 20 and the sum of the first 4 terms is 1640. Write the general term of each sequence. So sum of the first 4 terms equals 1640, which according to the formula means u1 times 1 minus r to the 4th, because we don't know the ratio and we don't know the first term, over 1 minus r. The sum of the first 2 terms equals 20, and again we can write the same thing, u1 times 1 minus r squared all over 1 minus r. If we divide this expression from that expression, we get a nice cancellation. u1 is going to cancel with u1, and 1 minus r is going to cancel with 1 minus r. And we're going to have to divide 1640 by 20. So all of that combined, we get 82, because that's 1640 divided by 20, equals 1 minus 4r, r to the 4th, over 1 minus r squared. Now we know that by difference of squares, this is equivalent to the following expression, 1 minus r squared times 1 plus r squared, all that over 1 minus r squared. These two terms are the same, so they cancel, and we get 82 equals 1 plus r squared. Minus 1 on both sides, we get 81 equals r squared, which means r is plus or minus 9. So that's where we get the two sequences. So now we can find the general term of each sequence. In order to do that, we need to figure out what is u1. So let's use this formula to figure out what is u1. 20 equals u1 times 1 minus r squared all over 1 minus r. I'm going to actually rewrite this using the same difference of squares trick, and that's going to be u1 times 1 plus r and 1 minus r all over 1 minus r. Again, these terms cancel, and so we have 20 equals u1 times 1 plus r. Now we know that r is either negative 9 or positive 9, so we're going to get two values for the first term. Let's figure them both out. 20 equals u1 times 1 plus 9, and 20 equals u1 times 1 minus 9. So this first one is going to give us u1 equals 2, and the second one is going to give us u1 equals negative 5 over 2. So with both of those, we can construct our general terms. Un equals 2 times 9 to the n minus 1, and the second one, un equals negative 5 over 2 times negative 9 to the n minus 1. Determine how many terms are required for the sum of the geometric series given below by this expression to exceed 1000. So our ratio is going to be 2. Let's figure out what our first term is. 3 times 2 to the 1, because we plug in I equals 1, gives us 6. Now let's set up our formula. The sum is going to be the first term times r to the n minus 1 over r minus 1. You'll notice that I wrote these backwards. That's actually an equivalent expression, but you'll see that in this question it's easier. So we want to know when is this going to be greater than 1000. So I can plug in my value of 2 for r and do some simplifying. On the bottom I'm going to get 1, and then if I divide by 6 on both sides, I get 2 to the n minus 1 greater than 167 or so. Plus 1 on both sides, 2 to the n is greater than 168. So we want to figure out when is this true. The first one's going to be 2, then 4, then 8, not 6, then 16, 32, 64, 128, and then 256 is finally bigger than this number. So that's 1, 2, 3, 4, 5, 6, 7, 8. It took 8 terms. Alright, that's it for this lesson. Now go ahead and try some practice on your own.